Hey, good afternoon, guys. I hope that all is well and you guys are doing good. What we're going to be talking about today is one of the most powerful tests you guys are going to have when it comes to series. It's called the comparison test. The comparison test, the direct comparison test, is actually very useful because if you know something it converges and it's larger than the series that you're looking at currently, then you know that it also converges. So for example, if you know that b sub n, the sum, the series b sub n added up from n equals 1 to infinity, if you know that that's larger than a sub n, then you're able to show if it converges, then the other one must also converge, being smaller. The same thing applies if the value over here of a sub n, if a sub n diverges, this is the vice versa. If you can show that you have something that diverges that's smaller than the series you're looking at, then the outside part of it also diverges. A little bit of a typo here on my behalf. Okay, so it works one of two ways. If the outside converges, then the smaller one must also converge. If the inside one you're comparing it to diverges, then the outside one must also diverge, okay? And that's the basic concept. Here's the first little example that I'm going to show you guys. This is the first little example, okay? We're going to go ahead and take a look at the harmonic. The harmonic series from n equals 1 to infinity, we know that this diverges, since it's harmonic. It's the P series, okay? Then we know that the series from n equals 1, why did I write 2? Oh, because in the next one I'm going to use 1 over n minus 1. n minus 1 from n equals 2 to infinity, the reason why I put a 2 here is because of that, must also diverge by the direct comparison test. The DCT. Now, why does this work? Well, we're looking at 1 over n minus 1, okay? We don't know if it diverges or if it converges at this point. We can go through and try to apply the integral test to it. We can do any of the other tests, or we can compare it to something, because if you look at it, it looks very similar to 1 over n. There's just this minus 1. And what do we know about 1 over n? We know it diverges. So this right here, we're going to let this be a sub n, and this be b sub n. And this is the basic concept, okay? Following the rule right up above. 0 is less than a sub n, is less than or equal to b sub n. And what we know is that a sub n diverges because it's a harmonic, right? If it diverges, any sum or series that's larger than it is also going to diverge, which is this part right here. So this one must also diverge. Why is it larger, do you ask? Well, if you think about it, when we're taking this number, we have to compare it. This is going to start off, when we plug in, we're going to get 1 over 2. If you plug in this one, we're going to get 1 over 1. If you plug in 3, you're going to get 1 over 3. If you plug into this one, you're going to get 1 over 2. So this is always going to be larger than that one by one term. And therein lies the direct comparison test. Okay, that's one side of it. We're going to show the other side as well. I'm going to give you guys a couple of reasons why the comparison test is needed, okay? So let's go ahead and look at a couple of these. Here's the first one. Here's some examples. These are some examples as to why a comparison test is needed. Okay? And so here's my first example. We have the sum from n equals 1 to infinity of 1 over 2 to the power of n. We know that we can write this as the sum from n equals 1 to infinity of 1 over 2 to the power of n. And this right here is a geometric. This is geometric. And r is less than 1. So it converges. Okay? This value right here is less than 1, so we know that it converges. Okay? But here's the thing. We have another problem. If you get something that looks like this from n equals 1 to infinity, if you have n over 2 to the power of n, this is not geometric. Okay? And so this is one of those cases where you want to use the comparison test to determine convergence for it. Okay? Why? We have this n on top. It's not going to fit an ln property. It's not going to fit a u substitution. We're going to have to go through and we're going to have to compare it to something. Okay? And so if this converges, what we're looking for is we're looking for this case with the comparison test where 0 is less than, I believe it's less than or equal to 0. It's less than 0. A sub n is less than or equal to b sub n for all values. And so what we're trying to do is show that this a sub n here converges, or this b sub n converges. Okay? And if this converges, then what we know is this a sub n must also converge since it's smaller. Okay? If it's smaller than a larger series that we know converges, then it must also converge because it's smaller than it. And that's one of those examples. Okay? We'll go a little bit more into depth when we do a few problems. Here's another one. If I have the sum from n equals 1 to infinity, sorry, I made an e there, of 1 over n to the power of 3. We know this is a p-series. And it converges since p is greater than 1. And we get that from this portion right here. We know p is greater than 1. Okay? But if I give you guys something that looks like this, the sum from n equals 1 to infinity of 1 over n cubed plus 1, this is not a p-series. And taking an integral of that's not going to be super fun. So this is not a p-series, so this is one of those cases where you want to compare it to 1 over n cubed. And it wants to follow that same property. Since the 1 over here, the larger value converges, then the smaller one must also converge. And that's kind of the basic idea, okay, of the comparison test. All right, so here's on to a few problems. I'm going to do the first one with you guys. You guys are going to do the second one, okay? And I might help you out just a little bit. Okay. So we're going to split this up into two parts. I might help you out a little bit with the second part and let you guys finish. Okay. So first off, when you're looking at this, we notice we have 1 over 2 plus 3 to the n. Okay, we don't know if this converges or diverges. Integral test, I don't know how to take the integral of 2 plus 3 to the n in the denominator like that. So we're either going to have to rewrite it or use a comparison test at this point, because once again, we know the geometric series test, we know the p-series, and we know the integral test. And the integral test right now, it doesn't look like something we're going to be able to do very easily. So what we're going to try is just pick something that we know converges. We're going to compare it to, in this instance, we're going to just pick 1 over 3 to the n. We're going to try to make it a little bit nicer for ourselves. Okay, so we're going to go ahead and compare this to the sum from n equals 1 to infinity of 1 over 3 to the n. If you want to rewrite this, we can rewrite this as the sum from n equals 1 to infinity of 1 over 3 quantity to the power of n. And what you guys know about this is a geometric series where r is less than 1. The absolute value of r is less than 1. So what this means that our function converges. So it converges. Okay? Now, here's the thing. We need to make it work this way. We need to set one of these to a sub n and one of these equal to b sub n. And essentially, we need to show that b sub n converges. And if b sub n converges, then anything that's smaller than it must also converge. And the idea is this one must also converge. Okay, so let's go ahead and try to write it out. Let's try to figure this out. First off, is a sub n, is this always smaller? Let's think. This is a sub n and this is b sub n. Let's think about the first few terms. If I plug in 1 here, I get 1 over 5. If I plug in 1 here, I get 1/3. Okay, so this is bigger. If I plug in 2, I get 1 over 11. And I get 1 over 9. So yes, this is always going to be smaller, so it does fit our test. And then we just have to go through and state it. So we say something along the lines of, since b sub n is greater than or equal to a sub n for all values of n, then the sum from n equals 1 to infinity of 1 over 2 plus 3 to the n must converge by the direct comparison test. And that's the basic idea. Okay? If we can show that one of these converges like we did right here, and it's always larger than our sum of a sub n from n equals 1 to infinity must also converge because it's smaller. Okay? We're going to do the same thing in this other one, and we're just going to have to start to think about things in terms of being bigger or smaller. And the question's always, how do I know what to go with? How do I know? And here's the basic concept. We're going to go and try to compare it to something. We're going to compare this to the quite obvious. We're going to compare this to the sum from n equals 1 to infinity of 1 over n to the 1/2 power, right? And so in this case, we know that this is to the power of 1/2. What does that mean? Well, this is a p-series. And we know that the value is less than 1/2. So that means is less than 1. So that means this diverges. Anything between 0, what do we call this? We call this r, is less than or equal to 1, diverges. Okay, so here's the basic idea. We need it to fit the format 0 is less than a sub n is less than or equal to b sub n. Okay, for this to work, we have to show that it's smaller always. And the idea is if this diverges, then anything that's larger than it has to diverge as well. This also has to diverge. Okay, and you have to state, just like in the last problem here, for what x or n values. Sometimes you want to write out a few terms of the sum just to see what's going on, okay? So in this case, if we do this one over here, we're going to get 1 over 2 plus 1, that's 1/3, plus 1 over 2 plus root 2, plus 1 over 2 plus root 3, plus 1 over 2 plus root 4, or 1 over 4, okay? And you guys can start to see some patterns as we go with it. Now, we have to show that this is a sub n. We have to show this is a sub n and the other one's b sub n. We have to show that the top function is always larger. And so let's just go ahead and plug in a few of these to see what happens, right? We get 1 over 1. It already fails. That's larger. Okay? Plus 1 over square root of 2. Larger. Plus 1 over root 3. Larger. Plus 1 over 2. Larger. So in this case, this is not going to work. This does not tell us anything. Does not work. So we need to compare it to something else. All right. Now, one of the sweet fallbacks that we're going to keep falling back on, guys, is we're going to just pull out the harmonic every once in a while and just see if it fits it, because we know the harmonic diverges. And so we just need to show that it's always going to be smaller than b sub n, which would be this part up here. Okay, this one doesn't work. We're going to go and try to make that b sub n. It always has to be larger. So let's compare it to the sum, the series, from n equals 1 to infinity of 1 over n. We know that this diverges since it's harmonic. Okay, and what we need to do is show that it's always smaller. Okay, this one's going to take us a little bit because it may or may not be smaller always. Let's go ahead and plug it in. First step, we're going to have 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Ha ha ha. That part, this is going to be our saving grace. You look at this fourth term, 1 over n is going to overtake it. It's going to grow faster because this is a square root of n. It's going to overtake it after the fourth term. We're going to get 1 over 5. And the other one's going to be 1 over 2 plus root 5, which is going to not be, it's going to be smaller after that. So b sub n is going to be, I think I said this correct. Yeah, I did. So we're able to go through and apply this. So since b sub n, am I writing this out correctly? So we just showed is that this is always going to be smaller after the fourth term. This is smaller after the fourth term. So this is when n is greater than 4. Okay, I'm sorry, I was saying it wrong. So what we know is that b sub n, or a sub n, is smaller than b sub n when n is greater than or equal to, or greater than 4. It's equal to it at 4. Okay, then what we know is the series, or the sum, from n equals 1 to infinity of a sub n diverges. B sub n diverges. Sorry, I wrote this incorrectly. B sub n diverges by the direct comparison test. Okay. All right. So this is quite a bit to process. This idea, once again, though, you have to map it out. And these two things right here, this and this, are the basic ideas of the comparison test. There's not much more to it. We're just trying to follow that pattern. Okay? All right. Now we're going to go on to a test that's called the limit comparison test. If you find that you cannot use the direct comparison test, why can we not use the direct comparison test sometimes? Well, you have to find a value that fits this, and sometimes you're not going to be able to run into it. So in the limit comparison test, this is what we do. Suppose that both of our sums are larger than 0. They're both positive, okay? And if you take the limit as n approaches infinity of this entire thing here, it approaches a number. L must be finite and positive. If this is the case, then both series must converge or both diverge. Then both series converge or both must diverge. Okay, so if you get a positive finite number when you do this, then it shows that both of them must converge or diverge. And so what you guys are going to do in this one is you're going to compare it to a series that you know, in fact, will converge or will, in fact, diverge. Okay? And if you do this, then if it diverges and the limit when you divide them exists, then they both diverge. And if one converges when you take the limit and you also get a finite positive number, then both must converge. So you want to pick basic ones that you know, like the harmonic or a p-series or something that you've done recently that you know converges and can prove it or diverge. Okay, so show the following general harmonic series diverges. 1 over a to the n plus b. Okay, let's take a look. All right, so what are we going to do with this? We're going to go through and we're going to try the limit comparison test. This is proving the general rule. This is for anything that's just 1 over n plus something. N to the power of 1, of course. What we're going to do is compare this to our favorite one. We're going to compare this to the general harmonic. N equals 1 to infinity of 1 over n. We know this diverges since it's a p-series where p is equal to 1. Okay? So because it diverges, if we take the limit comparison test, which once again you take and divide the two and you take the limit, then what we're going to end up doing is go and we're going to take this limit as n approaches infinity of a sub n divided by b sub n. And we're going to see if it approaches a value, a number. Okay? So we're going to take 1 over a sub n, a times n. I forgot to write the limit. The limit as n approaches infinity of 1 over a times n plus b divided by 1 over n. Okay? This looks like something we're going to want to multiply by the reciprocal of because we have a fraction over a fraction. So we're going to take the limit as n approaches infinity of 1 over a times n plus b times n over 1. All right? And when we do this, we're going to have the limit as n approaches infinity of n over a times n plus b. It's not a 6, that's a b. All right, now what we know is this is going to approach infinity over infinity. It's an indeterminate form. So what do we have to do? We have to apply L'Hopital's rule. And when we do this, we're going to get the limit as n approaches infinity of 1 over a, where a is a constant. So this limit's actually going to give us 1 over a. And what does this mean? Well, if you get a value, once again for that limit, if you get a value that's positive and finite, then what's able to happen is we're going to get that both of these must diverge by the limit comparison test. How do we know that this is positive and finite? A is greater than 0. That's how we know. It's going to be greater than 0. It's going to be positive. All right. And so as a result of this, we're able to say since the limit as n approaches infinity of a sub n over b sub n equals 1 over a, which is some value L, then we know the sum from n equals 1 to infinity of 1 over a sub n plus b must also diverge. Must also diverge. And that's the basis for this. I should have put a little part over here that we compared to the harmonic, but that's about it. Okay. All right. So the limit comparison test works well for very messy algebraic series with p-series. In choosing an appropriate p-series, you must choose one with an nth term of the same magnitude. Generally what you do is you look at these when you're doing this comparison test, and you normally go through and you pick the same degree in the denominator. You want to go through and make sure you have the same basic concept. Over here on the left-hand side in the second one, we have square root of 3n minus 2. The overpowering factor is the square root of n. That's what's increasing. It's going to overtake everything in the denominator. So we're going to compare it to that. And you want to follow the same thing. When you're doing this as well, if you look at this problem, we have n squared, n to the 5. So what we're going to do is subtract those, and we're actually going to be able to compare this to 1 over n cubed, which is going to be it's a p-series where n is greater than 1. So it works. Not n is greater than 1. Our exponent's greater than 1. So it works. It's going to converge. Okay. Now we're on to the kind of last little bit. This is the same sort of problem we're going to want to work through. I'm going to give you another example after this that you guys are going to work on that's not on your set of notes. But we're going to do the same thing. Okay? What we've learned is we're able to compare this to something that's very close to it. If you look at it, the overpowering factors that are here, we have n times 2 to the power of n, and we have n cubed. So I'm going to try to compare this to, compare to the sum from n equals 1 to infinity of n times 2n all over n cubed. Right? We know that we have this n in our numerator and we have an n in our denominator. So we're going to get 2 to the power of n over n squared. Okay? And so with this, we have 2 to the n squared. What's super nice about this is we know that the numerator is going to grow way faster than the denominator. So we're going to apply the nth term test. We're going to go through and apply the nth term test to see what's going on. Okay? If we take the limit as n approaches infinity of 2 to the n over n squared, we know this is going to give us infinity over infinity, right? So we have to use L'Hopital's rule. L'Hopital's rule. Okay, and when we do this, we're going to get the limit as n approaches infinity of 2 to the n times ln of 2 over 2n. Okay, this is also going to give us infinity over infinity. So we have to do L'Hopital's rule again. And so what ends up happening is we're going to have the limit as n approaches infinity of 2 to the n times ln of 2 times ln of 2 over 2. And when we take this limit, we're going to have this approach infinity, which means that this diverges. Okay? So we know that what we're comparing it to diverges. So we have two options. We can do the direct comparison test. And if we do the direct comparison test, we have to show that 0 is less than a sub n is less than or equal to b sub n, we have to show that a sub n is always smaller than b sub n. And if a sub n diverges, then anything that's bigger than it must also diverge. I don't really want to go through and look at this and compare all of the terms, see if it's always going to be smaller than our original series. So what I'm going to do is I'm going to go ahead and apply the limit comparison test. The limit comparison test. And what this is going to require is for me to take the limit as n approaches infinity of a sub n divided by b sub n. And this is going to look a little gross at first, but we're going to take the limit as n approaches infinity of n times 2 to the n over 4n cubed plus 1. Quantity divided by 2 to the n over n squared. And we're going to have to multiply by the reciprocal. So we're going to have the limit as n approaches infinity of n times 2 to the n over 4n cubed plus 1 times the reciprocal, which is n squared over 2 to the n. What's nice about this is the 2 to the n are going to cancel right here and there. And we're going to be left with this right here. We're going to be left with the limit as n approaches infinity of n cubed over 4n cubed plus 1. Well, we notice that this is going to, both when we take L'Hopital's rule 3 times, it's going to cancel out, and we're going to be left with 1 over 4. Okay? And so since we found a limit that's positive and finite, then we know that both the things that we compared, this right here, this series, and this series must both converge or both diverge. And we found that this one diverges, so it means that our original also diverges. Okay? And we wrote that out not too long ago right here, where we had to go and say, since the limit approaches a value, the series that we're comparing it to diverges, then the other one must also diverge. And that's kind of the basic idea for it. Okay? All right. I'm going to give you guys one problem. I'd like you guys to try this one out on your own before you guys attempt your homework. Let me go ahead and write this out. I want you guys to do the limit comparison test on this. Or you can do the direct comparison test. I believe both will work just fine. But here's another example. We're going to call this example number 4. What I'd like you guys to do is take the sum from n equals 1 to infinity of the square root of n over n squared plus 1. Okay. I'd like you guys to please try this out for me. If you guys are having an issue trying to figure out what to compare it to, please take a look back at this third section right here on our notes. Take a look back here at this third section on our notes and try to figure out what you guys are supposed to do. Okay, so go ahead and try this one out. Determine if it converges or diverges. And that's it. I hope you guys have a great day. Bye.